Okay, so the video wouldn't continue recording. It just kept on a blank screen. So as I said, that was a good spot to stop at. You're not missing anything. I had just erased the board, and all I'm gonna do is record all of my results over here. I started writing them when I noticed the screen stopped recording. Okay, so not much difference from where the break was. So g of two is 0. G of 3 we found to be negative 1/2. G of 4 ended up being, let's see, was 0. G of 5 was, let's see, 3/2. G of 6 was 4. And G of 7 is approximately 7. Now what it wants us to do with this is graph this function, okay? Remember, if we take a derivative, we get another function back, we could graph that function, okay? So now we've got a integral function, let's graph this function. So that's what it's saying. It says, where does g have a max value, where does it have a minimum value? Sketch the graph of g, okay? So let's first sketch the graph. See, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. See, go up 1, go up 2. I'm going to have to scoot this graph down. Oops. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so at 0, I'll do it in a different color. At 0, we are at 0. At 1, we are at 1/2. At 2, we are back to 0. At 3, see, if there's negative 1, you're at, let's see, 0, you're at 0. At 1, you're at 1/2. At 2, you're at 0. At 3, you're at negative 1/2. At 4, you're at 0. At 5, you're at 3/2, so 1.5. At 6, you're at 4, so 1, 2, 3, and 4. And then at 7, you're at approximately 7. So you can see the graph of g goes something like that. Okay? Goes something like this. So on this interval, it asks us, where does g have a minimum value? Well, it has a minimum value right here. Has a minimum value of, this is negative 1/2. Now, if we're talking about this closed interval here would be the absolute maximum right there of approximately 7, because we estimated that last piece. Right here would be the local and absolute min, and right here we would have a local max. Let's see, we could do this in terms of critical numbers too. Okay? If we look at, oh, sorry, not critical numbers. It goes increasing to back down to 0. So if we're increasing back down to 0, if you think about Rolle's theorem, there has to be a minimum or maximum value on that interval from 0 to 2. 0 to 2, you see, we got a maximum. Same with from 2 to 4. From 2 to 4 fits the criteria of Rolle's theorem. There has to be a minimum or maximum. We have a minimum there. Okay? So the fundamental theorem of calculus part 1 states that we can rewrite the integral as a function of x. Now, something else we can do with the first part of the fundamental theorem of calculus is to find the derivative of an integral function. So let's see. the instructions, I don't want to use this marker, says use the fundamental theorem of calculus part 1 to find the derivative of the function. So we're going to find the derivative, and here's our first example. G of x is equal to the integral from 0 to x of ln 1 plus t squared dt. Now, if I were to find the derivative of this function, as we mentioned earlier, derivatives and integrals are inverse processes, okay? The integral is going to undo a derivative is going to undo an integral, okay? Now, we're taking the derivative with respect to x, okay? The derivative and the integral are going to cancel out. When they cancel out, you have to plug in your endpoints, but when you plug in your lower endpoint, it's just going to give you a number because you're plugging a number into a function. And then when you take the derivative of a number, it goes away. But then you got to plug in this upper endpoint into this function, okay? Now when you do that, you're taking the derivative with respect to x. This is where your variable is. You have to watch out for the chain rule. When you take a derivative, you take the derivative of the function with respect to your variable, and then you got to multiply it by the derivative of the inside. This upper piece right here is the inside of your function. That is where you may find where you need to do the chain rule on. Now, when you take the derivative of x, it's just 1. So in this example, we're not going to need to do the chain rule. So we're just using the fact that the derivative is equal to the function at x. So that just means that get rid of the integral sign, get rid of the derivative sign, plug in x for everywhere you see t. Get rid of the dt. That's all that is saying. When you want to find the derivative of a function that looks like this, an integral function, the function and the derivative cancel, and you evaluate your function at this upper limit. So the answer to this right here, so let's see, d by dx of g of x, which is equal to g prime of x, is equal to d by dx of this 0 to x ln of 1 plus t squared dt. Well, that is equal to ln 1 plus x squared, and that's it. This right here would be your f of x. So g prime is equal to f of x right there. All I did was take this x, plug it in. Let's take a look at the next example. It says h of x is equal to the integral from 1 to the square root of x of, let's see, z squared over z to the 4th plus 1 dz. So we want to find d by dx of h of x. So in other words, we want to find h prime of x. So we want to take the derivative of this function. Well, the derivative of this function, remember, you're going to plug, if you plug in 1 into here, into the function, you just get a number. But then if you take the derivative of a number, it goes to 0. So we don't have to worry about this lower limit. We just got to worry about this upper limit. Now what you do is you take the function itself, you plug in this upper limit. So I get the square root of z, sorry, not square root of z, square root of x squared divided by square root of x to the 4th plus 1. But now multiply it by the derivative of the inside. This x up here, whatever function is up here, that is your inside function. In the previous example, it was just an x. So the derivative of an x is just 1. So we didn't have to worry about it in the last problem. Here it's a square root of x. The derivative of square root of x is 1/2 x to the negative 1/2. Now you just got to simplify. Square root of x squared is just x divided by, let's see, we've got a 2. We've got a square root of x on the bottom from that piece. And then square root of x to the 4th is x squared plus 1. Let's see, you could simplify this a little bit. These two pieces can simplify, and you would be left over with square root of x over 2x squared plus 1. So it's very important you remember to take the derivative of this inside function up here and multiply it after you plug those in. Really simple concept. Most of the time students forget the derivative of the inside, the chain rule. Let's go ahead and do another example. Let's see, it says y is equal to integral sine of x to 1 square root 1 plus t squared dt. I want to find y prime, that's dy dx. Take the derivative of this function. Now before I do that, if you notice something on this function, the limits of integration are switched. The function, the x value, or yeah, the variable is down here at the bottom, the number's on top. In all the other examples, it was always switched. The number was on bottom, and the function was on top. So I'm going to rewrite that. But when I switch the limits of integration, you got to remember the properties that we went through in the previous video that produces a negative sign out front. Okay? So now if I take the derivative of this, so I got negative d by dx of the integral from 1 to sine of x, square root 1 plus t squared dt. Well, the derivative and the integral are going to cancel. The derivative of a constant is 0. So all I have to do is take this function, plug it in. So I got the negative on the outside, square root 1 plus sine x squared, just take sine of x, plug it in. But now I have to remember to multiply this function by the derivative of this inside function right there. The derivative of sine is cosine. So the final answer, if I just bring that cosine out front, negative cosine of x times the square root 1 plus sine squared of x. This would be your answer for the derivative of this y function right here. All right, so you should take a pause for a second. Go ahead and try that problem that I gave you. It's much like the very first problem that we did for using the fundamental theorem and calculus part 1 to find the derivatives.